today we will talk about MLE for classification. So let's think about we have two classes, 0 and 1, maybe non-cancer people, cancer people, right? Okay, so that's a that's classification task, right? So in maximum likelihood estimation, we have a P. We want to maximize PR. We are given X and the parameter theta. Actually, we have a training data, right? In training data, we have n number of examples. So I should do this summation. Actually, this doesn't matter. This is just a constant. Okay, I should do this. Sorry, this is not summation. This should be a product. So this is maximum likelihood we want to solve for all the supervised learning algorithm. Now for in linear regression, for regression problem, what we do is we assume epsilon as a follow normal distribution. Then we can assume the y also follow the normal distribution, right? And here we assume the y follow a Bernoulli distribution. What is Bernoulli distribution? Bernoulli distribution is like we have a random variable. Here the random variable is y, right? So I have a probability of p. The p is a probability of the random variable equal to a target label. Maybe here is 1, right? So the distribution function would be p 1 p. So then this is the distribution, okay? Why does this make sense? Why this function makes sense? Think about it in this way. If you have y equal to 1, what's the value of this? The value would be p1 times 1 minus p is equal to p, right? This is definition of p, right? The probability of y equal to 1. When y equal to 0, it would be p0 times 1 minus p. 1 minus 0 equal to 1. So here is 1, here is 1 minus p, so it's equal to 1 minus p. Makes sense, right? We only have two outcomes. If the probability of y equal to 1 is p, the probability of y equal to 0 should be 1 minus p. Makes sense, right? So this distribution makes sense, right?
Can y could be any other number also, or it could be always 1 or 0?
It can only be 0 and 1. This is a binary classification, but I think you want to talk about the multi-class classification, where the number of classes is larger than 2, right? Is what you are talking about?
Yeah, could be. Like I not read about that thing, but yeah, I just thinking like could there will be more than 2 classes?
Yeah. Actually, if you do this, this can be generalized into the more than 2 classes models. For example, if you have 3 classes, 0, 1, 2, you can also use this. You can also turn it into the binary classification problem. How? You can make this. You can make 3 kind of sub model sets. Whether this example equal to 0. So now if 0, then it becomes a binary classification, right? If it's yes, it's 1. If it's no, it's 0. Same for the 1. If it's you ask this question, whether this example belongs to the class 1, then you have a 0 and 1, yes or no of yes. Same for this, okay? So it can be generalized to multi-class classification. If I think I will, yeah, I may will talk about this in later. Depends on you. If you still want me to generalize this binary case to multi-class classification, I will show you how to generalize it. I mean, in the code, in a very implementation details. Okay, so now we have this. Now we can get the likelihood function, okay? What's the likelihood function now? It become this. P1 minus P 1 minus 1. Okay, so let me erase. Let's have a look at this. So we need to solve this. If we want to solve this, I think I can simplify this first. Remember, if we want to maximize this likelihood, is equal to minimize the negative log likelihood. So actually, it's equal to summation rather than product of y. Let me get log. I will do it from scratch so you can get to the detail. See, these two are same, right? Because I put minus 10 here. That's why maximum become minimum. And I put log here. Log doesn't affect the direction of the whole function. So it doesn't matter. Then, well, how I can simplify this? This is a log function. You should remember the log x a equal to a log x, then log a b equal to log a plus log b, right? So we can use these two rules to simplify this. Now simplify. Now use the second rule first. Log p y plus log y minus p y minus y. Now use the first rule. I will put y at the beginning. Do the same thing for this. I will put y minus y at the beginning. Okay, so all good? Okay. Yeah, let me. Okay, so now we do the 1/3 of the work. This is 1/3 of work. We have another 2 work we need to do. One, we need to apply this into the logistic regression scenario. That means we want to, we know what's a y, right? Sorry, this is yi, ti. Just the p. We know what's a y, but we don't know what's a p. So we want to use the logistic regression to replace this p. So yeah. Then if we can do that, what we need to do is, as what we did last week, we try to use algebraic approach to solve this. We just make the derivatives equal to 0. Let's say if we can solve the problem to get the parameters of logistic regression. Okay, so let's do it. So, okay, what's a logistic regression? Logistic regression is similar to linear regression because it has linear function. But what make it different from linear regression is it has a sigmoid function applying to the output of the linear function. So that will be the prediction. So this is a function of logistic regression. So what's the sigmoid function? Sigmoid function is, if I say this is equal to z, let me put z equal to beta 0 plus beta 1 x. So then this would be y hat, okay? So here is 0, here is 1. So the output always between 0 and 1. It will approach 0 on the infinite side. It will approach to 1 on the negative infinite side. It will approach 0. On the positive infinite side, it will approach 1. Okay, so this is a sigmoid function. So this is so in this case we can assume it's a probability, right? Because it's between 0 and 1. That is the key idea. In logistic regression, we assume the output is probability of the target label. So the probability of target label in Bernoulli distribution is p, right? It's p here, right? So now we can substitute this p with the parameters with a function which contains the parameter of beta and beta 0 and beta 1. That's what we want to solve, right? Remember, in linear regression, we want to get the optimal value of beta 0 and beta 1. It's kind of same as linear regression. Okay, so now we will kind of finish the second task. Let me formalize it. Now, what the objective function is, we want to minimize this negative log likelihood. Where we have yi, the true label, and we have p. P actually is this, right? It's y height. Then we have plus y minus y log y minus y height. Okay, so Okay, we resolve these two tasks. Let me erase it. The final task we want to resolve is use algebraic method to get the values of beta 0 and beta 1. Now let's resolve this. Derivative, right? Same thing. This is function, let's call function f. What's the function f is equal to, sorry, not equal to. We want to get the derivative derivative of this function with respect to beta 0 and beta 1. So we use chain rule to make it simpler. It's equal to, this is lambda f with regard to the y height and y height with regard to the z. Then we have z with regard to x. Okay, that's a chain rule. So let me resolve it one by one. Firstly, let me resolve this. This is easier part, right? Because it's a linear function. So if for beta 0, it would be 1, right? Because the constant is 1. For the beta 1, it will be x, right? Because the constant is x. So now we resolve this. This is easy. Now we want to resolve maybe this one. What's this one? This one is sigmoid function, right? Let me resolve this one. This y height z. What's this sigmoid function? This sigmoid function is, let me write down this sigmoid function. It's y plus e minus z 1. This sigmoid function. Okay, have a look of these steps. Can you see my screen now?
Basically, screen is visible, but the top portion of the blackboard is not visible.
Oh, sorry.
Yeah, now it's visible. Thanks.
Yeah, no worries. Let me explain this. Please remind me if you can't see just interrupt me if you can't see the whiteboard. So this is a lossy regression form. You have a beta 0 plus beta 1 x, then you apply the sigmoid function here. So, yep, what's the sigmoid function? The sigmoid function is this. I will put the derivative at last. Okay, this is the sigmoid function. So, yep, and for this one is between 0 and 1 because we apply sigmoid here. So then if it's 0 and 1, we can assume it is the probability of y equal to the target label. So we can replace the p from the Bernoulli distribution with this y height. So then we get our final objective function, right? So now we can calculate we want to calculate the derivative with respect to beta 0 and beta 1. One thing why we can do that, because this function with respect to beta 0 and beta 1 actually should be convex. I never proved that, but just remember, just assume it can be convex. Then we can go forward. Okay, so we resolve these derivatives. Now we need to resolve this derivative for sigmoid function. Oh, good. Okay. Yes, it's the correct form. To resolve this derivative, we need to make another chain rule. To apply chain rule to this, we want to make u equal to 1 plus e z. So let me write it using different color. U equal to 1 plus e minus z. So now we can see this equal to minus should be minus y height minus u minus c. Okay, then it would be easy, right? Because what's this? With respect to u is this is u, right? So this is 1 over u. 1 over u. What's this? U with respect to this. Is this right? So it would be z. Then I put this here. Okay, let's resolve these two derivatives. Then we can resolve this. Okay. So how to resolve this? This is actually a u1 u to minus 1. So the derivative of this is you put minus 1 as a constant, then you put u minus 1, right? So it's minus 2. So here u equal to minus 1 over u square. Okay. So for here, you have E minus C. Actually, EZ equal to the derivative of EZ equal to EZ. But we have minus sign here. So we also put the minus sign as constant. Then we, because EZ equal to EZ, here is E minus C. Okay. So this is the derivative. Then what's the then we put the original form back. So u equal to 1 plus E to minus C, 1 plus E to minus C. Okay, we got this. Remember, this is multiply, right? So we have negative multiplied by negative equal to positive. So we just erase this. So now we can, any problem for this? If no problem, I will erase, this middle content. So good. I will erase the intermediate content. So we have more space to go forward. Now I will directly get the result of this equal to 1 E times E C. Okay. So let me further simplify this. This equal to E plus E minus C, E minus C. I want to plus 1 here. Then I will minus 1. So it will be equal, right? But I can do why I do this, because then I can do something like this. 1 minus E C. I think I missed some. Oh, sorry, I missed the square. Let me go back to the previous form. Remember, I have a 1 u square. Actually, I missed a square here. I need to put this square back. So it would be minus E C. If I put this square back, it would be, remember, u is equal to 1 plus E minus C squared times, as before, I will erase the negative because we have 2 negative here. So now what's the final result? It's same as before, but the only thing we have the square here. So you can see here. Okay, so this should be the final result. Okay. If I go from here, then I will plus 1, minus 1, then I will get something. This is, I will do step by step. I will minus E. Okay, it's this. So why we need this form? Because we can simplify it. It's 1 minus E minus C. Here 1 plus E minus C. So I can erase it, cancel out with this square. So we can get this, right? So for this second term, what we can get is this is 1, so 1 equal to 1 square. So we can get this. We can put the square for both of for the denominator and the numerator. So all good. So then we can get something. What's this? This is a sigmoid function. So we can get this is sigmoid function of C. This is also sigmoid function of C. So now we can get the result equal to sigmoid minus sigmoid square. I put 1 sigmoid outside is equal to sigmoid plus not plus multiplied by 1 minus sigmoid. Okay, finally, I finished this derivative. So, okay. So this is this. The last derivative we need to resolve is this one. So let's resolve this one. This one is this, right? No. I eliminate the summation in this function, so to derive the derivative, because the summation of derivative equal to the derivative of summation equal to the summation of derivative. So I will put the summation back, but now I will I just eliminate it. So let's do it. It's y height. So this function equal to y time multiplied by log. I also eliminate the I at this stage. I will put it back later. Equal to y height plus y minus y times log y minus y height. Okay, so let's resolve this. to resolve this, we need to know what's the derivative of the log function. I think, let me check. Yeah, it's this. I will tell you the derivative of log function, log s equal to 1 over x. This is the derivative of log function. So now we can get the result, right? Here is y hat, not x. So it's 1 over y hat. This is constant, so I put a constant here. So same thing here, right? We have but we have log of 1 minus y hat. So we have put the minus 10 at the beginning. Then we do the same thing, 1 minus y hat, 1 over 1 minus y hat. Then we have 1 minus y here. So I will put it as a numerator. That's it. So I also put this y as a numerator. Okay. I think that's a final form. Let me have a check. Yeah, but that's the thing. Okay, well, good. Remember, we have negative side here. I don't include the negative side in this function. So to align with this, I should put the negative side here. Okay, that's it. But I still need to simplify this. Let me simplify it. The thing I want to simplify is this: y height plus. It's easy to simplify. You just multiply y minus y height at the first term. So you also multiply y minus y height at the numerator. Here's minus sign. Then here I multiply y height. So right, 1 minus 1. If you expand this, it would be minus y plus y height minus y height, plus y height minus y height y. Then you have denominator. Okay, so the key thing is we can eliminate these two because they are same, one positive, one negative, so we can eliminate. So what's the final star we have is minus y plus y height is equal to y height minus y, right? Y height minus y. Okay, so that's it. We have this. Okay. Now let's substitute the this final things into these derivatives. Let's see what we get. We have for y height minus y height times y minus y. Okay, we have these three terms. So what's the sigma z? If you look at the definition of logistic regression, y height equal to sigma z, right? So this is y height. This is y height. Y height multiply y minus y height. Actually, is the thing here. It's same thing. So we can eliminate these two. So finally, what we have is only this term here and this term here. So let me write the final stuff. Y height, y. If this is for beta 0, it should be 1. If it's for beta 1, you should multiply by x. Okay. So good. That's it. Let me erase this. Erase this intermediate. Okay. Let me split it. If it's I will put it as what we had is beta f, this objective function with respect to 0 equal to y high minus y. Beta f with respect to beta 1 equal to y high minus y times x. One thing I said, I will put the summation back. I will also put the I back, right? So let me put the I and summation back. Summation I equal to 1n. This is I. This is I. Equal to summation I equal to 1n. This is I. This is I. This is I. Okay, well, good. Do we give the result? Let's look at it. Do we give the result? We know what's yi, right? We also know what's the xi. This comes from training data. But what's the y height? Y height is a prediction of logistic regression model. It's y height equal to sigma y beta 0 plus beta 1. So no way, we can't resolve this in algebraically. So no algebraic solution. What should we do now? Let me clarify. These two still useful. You know, if they are not useful, I won't take so much time to derive these two. It's still they will be useful. But how can we make use of this too?